So this is going to get us started on our lecture number 22. Oops, there we go. Lecture 22. And if anybody can keep track of any sort of dates anymore, this lecture is for Wednesday, the 25th of March. So what we're going to focus on here is the 9th section of chapter 29, the magnetic forces on current carrying wires. So before you get started on this lecture, you should probably stop and have a read through the textbook, pages 820 to 822. Okay, so let's look at what is the magnetic force on a current carrying wire. And we'll start with the idea that we know there has to be a magnetic force on a current carrying wire. And that was something we did in a lab in Physics 1051. We made the little copper coil, we hooked it up to a power supply so that the current flowed, we set it on top of a couple of disc magnets, and we saw that it spun. So there is definitely a magnetic force on a current carrying wire. So let's see if we can develop what that equation is based on what we've already done for the magnetic force on a moving charge. So let's write that one down first. What is the magnetic force on charge Q that moves with velocity v in a magnetic field B? Well, that force is Fb equals the charge Q times the cross product of the velocity and the magnetic field. So that was something we covered in the previous section. Let's remember that velocity is change in position over change in time. So this could be written Q times delta x over t crossed with the magnetic field B. Okay, so let's just think about this a little bit more. We've kind of got a leading question down here. What is current? Well, current I is charge over time. And then the last thing we can look at is what do we mean by delta x? Delta x is how far the charge moves. It's the distance over which the charge moves. How far does the charge move? It moves the length of the wire. So if we put these things together, we get an equation for the magnetic force on a moving charge. Fb equals I, current, times L, length of wire, crossed with magnetic field B. One thing that's kind of important here, we put our vector sign on top of L for length of the wire. We could have just as well put it on top of the I for current. So we'll say that the direction of the vector L is defined as being the same as the direction of the current. So if this is a cross product, we know how to do those mathematically. It means we can use a right-hand rule to figure out the direction. Got a picture of the right hand over here. If you were going to use a right-hand rule to find the direction of force, then you point your thumb in the direction of the first vector, so I or L. So your thumb goes in the direction of the current, your index finger goes with the magnetic field B, and your extended middle finger shows the direction of the magnetic force F. So we can use that right-hand rule again. It's always the first one, cross the second one, gives the third one. That's how a cross product works. Okay, let's do a really quick example. Let's think of 3 wires. Let's put parts of them each in a magnetic field and ask what happens to the force. And if we can figure out what happens with the force, can we figure out what happens with the wire? So let's make our first one really simple. Let's have this wire not carry any current at all. What happens if I equals 0? Well, then FB equals IL cross B. If I is 0, then the force is 0. So we know that magnetic force only exists on moving charge, so there has to be a current in order to get a force. Okay, that one was easy. Next one, let's have the current, but let's make it flow down the wire. So I equals down. So let's draw that current on our wire. So there's our current I. Let's see if we can figure out the direction of the force. We put our thumb in the direction of the current, our finger in the direction of the magnetic field, and our extended middle finger shows the direction of the force. So it's pointing to the right. So our magnetic force, and I'll do that guy in red. And if there's a force on that wire to the right, what's going to happen is the wire is going to bend to the right. So that was I equals 0. That was I pointing down. Next, let's ask what happens if the current flows up. So now in our wire, the current goes straight up. There's our current I. Let's see if we can find our magnetic force. Our thumb goes with the current. Our finger goes with the magnetic field. Our extended middle finger shows the magnetic force. It's pointing to the left. So let's draw that force on there. If our wire feels a force that points to the left, then that wire bends to the left. Okay, so that's an overview of what happens with the theory. In the next part, we'll do a couple of examples looking at some forces on some current carrying wires.